So I explained pseudocode in a previous video, and so in this section I'm going to use pseudocode to explain the R code that we're going to use. And you are going to provide code, write your own code where I don't provide code for you. So if we think about the steps we have to follow if we want this answer, so we care about this IP10, the unstimulated IP10 variable, and we want to know, is it different between males and females? And we have a sample that is mixed. So our sample is mixed, it's got males and females. So what I say here, step 1, first find the difference in the statistic you chose for males and females in your original sample. So that's from the previous question. One of the previous questions was, which statistic are you going to use to decide whether males and females are different in terms of their IP10 value. So let's say we chose the mean. I'm going to use the mean IP10 and see whether the mean IP10 is different between males and females. So that's what I'm talking about here. We first find the difference in the statistic you chose. So if I chose the mean, the difference in the means for males and females in your sample, my sample. And then I provide code for you. And in the code there's this, it says here, your statistic, and you have to delete that and replace it with whichever statistic you chose. So with the function that calculates that statistic. So in my case, if I chose the mean, I'm going to delete your statistic here, and I'm going to write mean there. We're first calculating the mean for females, and then calculating the mean IP10 for males, and then I'm subtracting the two. So here's a new function that you haven't seen before, so I just want to demonstrate that. So filter is a function that takes this object, my sample, that's the first argument. It takes it, and then the second argument here that says sex equals f. So this sex is another variable in my sample, in the object, and the equals means, it just means equals to. It's just the syntax of R that you use two equal to signs. If you can't see well on the video, these are not dashes, these are equal signs. And then F is the code for female in your data. So if you look back at the data dictionary I provided, you'll see that F is for female. So when we run this line of code, you're going to see what happens. So TMP is just, it's a name I like to use. For me, it just stands for temporary. So I'm just creating quickly a temporary object that I'm just quickly going to use, and then I won't use it again. So if I run this line of code, we now created this TMP object, and if we look at it, if I just run the name, as usual, we see only the first 10 lines, so we're not looking at all the lines now, but from the first 10 lines, you can see what the function actually did. It chose all the rows of the my sample object where sex equaled F for female. So it chose only those rows. So basically what we did is we just created we took a subset from the my sample object, and the subset contains all the females. So that's basically what we did. And then what we do in the next line, where you are now going to replace it with your statistic, in my case mean, I'm taking this new object that I created, this subset that contains only the females. I'm using the $sign to choose only a specific variable, IP10 null. And you'll see here, it's somewhere here. And I'm going to take the mean of that. I'm going to save the answer I get from that whole operation into an object that I'm just going to call F for female. And then I do the same thing for the males. I use the same function, filter. As you can see here, I give it the same name as the one above. So that means I'm overwriting this object. So when I run this line of code, and I just look at it again, you'll see the difference now. So these are now all the males. So the first object that we created here doesn't exist anymore now. We overwrote it. And then we do the same thing. We calculate the mean of the same variable. We save it as m. And then we go on here and we basically take the difference. So I said f minus m. So in this case, f is the placeholder for the mean that I calculated over here. And m is the placeholder for the mean I calculated over here. So if I say f minus n, so R understands minus, plus, multiply and divide. So if I say f minus m, I created this object which I called diff my sample, and if you have now run all this code and you run diff my sample, you're going to get some value, just one value, which is now, that's what we did. We calculated what the difference in IP10 was for females and males in our sample. So that was step 1 that we have to do, because remember, we are trying to find out if IP10 is different for males and females. And so our first step is to use the sample that we have. So we find out what is the mean difference, or the difference in the means in our sample that we have. And that's what we calculated now. But as we said before, we're not actually that interested in our own sample. We're interested in what it means for the bigger population that we care about. So when we calculated this difference, that is the first step, but we can't just stop there. We're not just going to take this difference that we got and say therefore, we now believe that this difference that we got between males and females, that is the difference, that is the true population difference. As we said, this is why we need statistics. We now need to bridge the gap basically between the value we got, the answer we got in our sample, and what we think that means for the larger population. So for that we need some sort of a value that tells us whether this difference that we got, whether it is what we would call a significant difference or not. So, as you can imagine, and as we've said before, if you imagine doing many experiments, you can imagine, and you'll see, if you look at this, if we were in a classroom together now and all of you did this calculation, and if you all used the mean, did this calculation and got a difference, I would have asked you to tell me what the difference is that you found, and you would have seen that you all got a different answer. Even if it differed only a little bit, by 1 decimal place or something, still you would have all gotten a different answer, because you have 20 different data sets, unique samples, basically. So that is the problem, that since you get a certain difference and now the person next door gets another difference, so which one is now closer to the truth? The point is, we have differences now, and you have one difference that you got from your sample. How do we know whether this is close to the true population mean? And so this is where, again, our resampling statistics are now helping us. So our question basically, if we go back to what the outcome is, I spoke here about find the probability of getting an estimate as extreme as your sample estimate by chance alone. And you heard exactly this phrasing before in the lectures as well. So the basic premise is we want to know if we just keep on randomly sampling from this population and we do these difference tests, how likely are we to get a difference of 20? And how likely are we to get a difference of 2? Because that's our question now. Like I said, if I asked all 20 of you to give me now the answers that you got, somebody might get an answer of 20, somebody might get an answer of 2, and some answers in between. And so, I mean, it's clear to you that when we take random samples from some population, we get different answers, because that's exactly what we did, and we'll demonstrate we got different answers. So which answers should we trust? Basically, that's what we are trying to figure out. And in statistics, nothing is black and white. So there isn't a black and white answer to say, well, you should trust the 20, but you shouldn't trust the 2, or whatever. Everything in statistics is about probabilities. So we're not going to give a black and white answer and say, this one is right and this one is wrong. We're going to give our answers in terms of probabilities. We're going to say, well, and to get a difference from a random sample, if we just take a random sample from the population to get a difference of 20, the probability of that is X. So we're going to work out what the probability was that we would get such a big difference. And we're going to work out what the probability is that we get a difference of 2, for example. And that's basically what this statement is getting at. So if I just take random samples from a population, I calculate the differences, and let's say I get a whole bunch of, let's say I do it 1,000 times, and I create that sampling distribution that we looked at yesterday with the confidence interval. When we were calculating a confidence interval, you remember we created that sampling distribution. So essentially that's what we're going to do again now. We're just doing it for a slightly different reason. But so if we take 1,000 samples, random samples from the population, we calculate the mean difference between males and females for IP10. We plot it, so we get that same sampling distribution. This time it's just not, last time we just calculated the mean of each sample that we took. But this time we're calculating the difference in the means. So the steps we already followed, we do that. We calculate the difference between males and females, and that is the thing that we save, and that's the distribution we're creating is of the difference. We spoke about probability when we were talking about the confidence intervals. You understand that there are different values in that. So, like I said, when we calculate the median in that population, that means the probability that any value that we get is going to be below that specific value that is equal to the median is 50%. So that's not rare at all, So if you get a value that's close to the median difference, let's say the median of this distribution we created was 2, and you got a value of, let's say, 2.1 or whatever, then you realize that the value that you got, the probability to get that value is quite high. It's not a rare value that you got at all if your value is close to the median difference. In this question that we're asking, find the probability of getting an estimate as extreme as yours by chance alone. And what we mean by chance alone is we mean if I do this many times. If I do this 1,000 times, how many times am I actually going to get something very close to this difference that I got? If you take 1,000 samples, the majority of those are going to lie around, the middle of the distribution, and the median is in the middle of the distribution. So the probability of getting a difference around 2, if the median is 2, is very, very high. So we're we're not surprised by that result. So if you get a difference of 2 and the median is around 2, then that's not a significant result, because the probability of getting that by chance alone is high. Whereas if we got a difference of 20, and we now work out with the permutation test, which is what we're going to do, we work out the probability of getting a value as extreme as 20 by chance alone. So those are important words, because we're saying, but with, like I said, with by chance alone, we mean taking many random samples. And how many times are we going to get a result as extreme as this? And if we work out the probability, what's the probability, or how many times from 1,000 experiments are we actually going to get a difference of 20? And if we find, actually only 5 times, if we work it out, and we find actually 5 experiments out of 1,000 is going to give us a result as extreme or more extreme as 20, then that's a low probability. That's the probability then is 5 out of 1,000. So that's a low probability. And so that is when we start saying the test was statistically significant, or the result was statistically significant, because we pre-specify, usually before the experiment, we have to pre-specify what cutoff we are going to use for statistical significance, and most of the time we use 0.05. So if the probability of getting a result as extreme as the one we got by chance alone is smaller than that 5% that we chose as a cutoff, that's when we're going to say this was a statistically significant result. So if I go back here to the code, so we worked out the difference in our sample. Now our next step is to determine, I'm reading over here, determine the probability of getting this value or something even more extreme by chance alone. We will do this repeatedly by shuffling the 6 labels. So and calculating the difference. In my case, the mean is what I'm going to use. So this is now a new thing to wrap your head around. And the easiest way to think about it is back to the bag of numbers. So we have patients, and they each have a number. And like we said before, if we imagine doing 1,000 experiments, it's like putting our hand, or if we imagine resampling 1,000 times, it's like putting your hand in a bag, pulling out the numbers, putting it all back, pulling out numbers again, and doing that 1,000 times. And that's how you would get a random samples from the same, or random resamples. That's how we did the resampling. So if we work with that idea, but this time, instead of putting the numbers into the bag, the numbers of the patients, we put the labels of whether they are male or female into the bag. So at the moment, each patient, represents a real patient, so they have a real sex of either male or female in this case. So if we put those labels, we just put those labels into a bag. So the whole bag is just full of M's and F's. And now we draw out 1,000 times labels. And instead of putting the right labels next to a patient, so if we have, like in your data, you can see you have an ID column. And so you can always in your data know that ID 34680 is male. But now instead of, we just break that link between the ID and the actual sex. So instead of doing that, we say, okay, for ID 34680, I'm now going to put my hand into the bag and just draw out. So randomly, you're going to randomly pick M or F. We're randomly shuffling the labels. And how we're shuffling it is by doing it like this, putting your hand in the bag and just randomly pulling out whichever sex label comes out. So we're shuffling it. We pay no regard to what the actual sex of the patient is. We leave that completely up to chance, just what you're drawing out of the bag. But we use the same patient. We use the patient's actual, the IP10 null variable. We use that value still for the right patient. We're not shuffling that. We're just shuffling the sex labels. So basically we do the same thing we did for our own sample. In the code here, you'll see the parts that are familiar. If I just create some space. So over here, you'll see this is exactly what we did before. Sorry, not that. This part is what we just did with our own sample when we were just calculating what our own sample in the real patients, what the difference between their IP10 for males and females were. This is exactly that line of code. And beneath for females and below that for males. So that is what we're going to do. But the only difference is that before we do that, we do this shuffling step that I was talking about. And sample is the function that we have used before when we were resampling. And this is basically the same thing. We're using the same function. The only difference here is that the sampling is now just happening in the sex variable. And that is what I just explained. It's like putting your hand into a bag and pulling out an F or an M for female or male. And we take this argument is the size argument, so it's the same as the size of the sample. And again, this is without replacement. So that's another difference between what we did before. Before we, in the previous exercise, we sampled with replacement. But in this case, we're sampling without replacement because we want the same amount of males and females. We want the same number of males and females. We just want to shuffle the labels. So that's all we're doing. We're not actually... we're not changing the number of males and females, like the ratio of males and females in our sample. So we're not sampling with replacement. But by doing this, we are still shuffling the labels. So instead of using the actual labels of our sample, we are just leaving it completely up to chance. So that's what we do first. And then we do the same thing we did for our in our sample, like I said, to calculate the difference. And over here, you can see we do the same thing. F minus M, so we're just calculating some difference. And then all of this is happening inside a for loop, which I explained before. So in this case, we are doing it 2,000 times. We're doing 2,000 random shuffles of the sex labels. So it's like creating 2,000 different samples of 400. And we're saving it inside this permute data frame, which you were going to create there in step 2. That was the second thing we were going to do. Just create a data frame to save our answers in. And that's what we're doing here. We're saving our answers into it, and like before, we're using this I over here. So in this case, R is going to replace I sequentially first with 1. We're going to create the difference for the first sample we created and save it in row 1 of this data frame. Then R is going to replace it with 2, 3, 4, all the way to 1,000, and in the end we're going to end up with the data frame with 2,000 rows, and in one of those columns we're going to save the 2,000 different differences we found. So I just realized that you might get an error with this code as I'm speaking, I realize you might get an error with this code. R is doing something strange to me recently when I use the square brackets in some cases. So if this gives you an error message that says something like it can't change a character vector to a numeric vector, or a logical vector to a numeric vector, if that error message sounds familiar to you, then don't use this line of code. Just replace this line of code with the one I typed here, which is basically, it does the same thing in R. We just use $diff and we just put the I in square brackets like that. So if you get that error, just replace this code. So I'm just going to comment that line out for now. I think you should probably use that second line of code. Okay, so that's what we then did. And then if you run just this name, you're going to see your data frame that you created. And it's going to have this column called diff, and in that column you're going to have the differences between males and females of IP10 for the 2,000 samples that where we shuffled the sex labels. As before, you're going to draw a histogram for that, and then lastly, our step 7 in the pseudocode is now get the p-value by finding the proportion of observations in your data frame that is more extreme or equal to the difference in your sample. So this is where we're tying it all together. Because remember, our question is, we have a sample, we calculated the difference, but our question is, what's the probability of us getting this difference by chance alone? If that probability is like 50%, then, this is not a surprising result and we're not excited really. It means there's a very high probability that we just get this difference by chance. And the implication of that is really in the population, there probably isn't a difference between males and females, because it's very easy to get it by chance alone, as opposed to the difference being due to sex, basically. So that's basically what we're getting at. Either the difference is just by chance alone, or the difference is explained by the fact that we are calculating it between males and females. So that's what we're trying to ascertain. Is the difference accounted for by sex, or is it just accounted for by chance? It's just by chance that we got this difference. So finding the proportion of observations. So if you think of the histogram that you now created, and as we explained before in the confidence interval section, we're trying to find the number of values that lie below the value that we got in our sample. And by counting those values that lie below or above it, depending on which side of the histogram you're on, whether you're in the lower tail or in the right-sided tail, depending which side you are, that's what more extreme means. So if your difference was a negative difference and you find yourself in the lower tail, then you are going to count the values that are lower than the value you got. But if your value is in the upper tail, you are going to count the values that are more extreme, and in that case, more extreme means higher, right? So it can all get a little bit confusing. Be awake, basically, while doing it. And so that's basically what we're doing here. We're saying in our dataset that we created, where we saved the answers in the diff column, how many, we're basically asking R, take each one of those values that we saved inside that diff column and evaluate each one of them and tell us whether that is larger than or equal to the difference we got. And now again this sign here, so what this sign here is, if you can't see well on the video, it's the greater than sign and then the equal to sign. And that's basically in R how you write greater than or equal to. If you want the opposite, then you just change it to the lesser than sign. So it's going to depend on which one you need to use. It's going to depend on the difference you found. So don't get confused there. But basically we're asking R, take each value in this diff variable of ours in which we saved our answers and evaluate for me whether it was greater than or equal to, in this case, the difference. So this is the object where we saved the difference for our own sample that we calculated first in this whole session. So evaluate each value there for whether it's greater than or equal to that difference. And save that in a variable called temp. And if after this, so if you create this, and after that you just write temp and you look at what you created, you're going to see a whole bunch of, you're going to get 2000 because this column is 2000 numbers basically. So you're going to get 2000 values, but in this case it's not going to be numbers, it's just going to say true or false. And that's basically the answer. That's what you asked R to do. You said, is the first value in this whole sequence of numbers or differences that we calculated, is it greater than or equal to the difference I found in my sample? And then if it is greater than or equal to, R is going to print true. If it isn't, it's going to print false. And it's going to do that for each value. So that's why this TMP object that we're creating is going to be the same length as this column. It's going to have the same number of values, 2000, but it's just going to be a bunch of true and falses. And so that is what's called a logical vector in R. It's a very specific thing. It has only true and false in it. And what is more is that R interprets it in a very specific way. So if it says true, R counts that as a 1. If it says false, R counts it as a 0. And because of that specific property, we can use the sum function on that. Even though it's words, when we use the sum function, R counts all the ones, basically. He sums up all the ones that it finds inside this object. And like I said, even though it says true and false, basically that means R is counting all the words where it says true, because those are the ones. So R is counting all the true entries in that variable, and we are dividing it by 2000 because we are looking for the proportion of observations that is more extreme or equal to the difference that we found. And so that's how we find the proportion. We count all the true values, we divide it by 2000, and then we're going to get a proportion. And this proportion that you get is the probability, and it is the p-value, basically, for the permutation test that we did. So you can continue and to answer these questions, because that's the answer you have to give. What is the p-value? You calculate it, and then you have to interpret it and decide whether you reject the null hypothesis.